NanoHub U, online instruction.
Hey everyone, welcome to lecture 419. So in the last lecture, we were just explaining how thermal radiation works in more detail. And now we're going to look at another potential application for thermal radiation besides thermography, which is thermophotovoltaics. And so this is a summary of what are some of the applications or uses of thermophotovoltaics. In one example, you could actually use this to generate power in a portable fashion, where basically you'd have some sort of like portable heat source, which could be biofuel that's being burnt. And then as that burns, then you can actually illuminate a photovoltaic diode to generate electricity. Another approach actually is to use the sun as a heat source. And here basically it's concentrating sunlight onto some sort of selective absorber. And then that's sent to selective emitter, which radiates onto the thermophotovoltaic diode. And then in the third case, actually, this could be used for remote missions. So say you're sending a probe to Pluto, like the New Horizons mission, then actually they can't really rely on solar panels because it's too far away from the sun. There's not enough power. So instead, they need some sort of portable thermal generator, which is actually supplied by a naturally decaying radioisotope. So think of your smoke detector. It actually has a very small amount of a radioisotope, so it's actually not dangerous to human body as long as it's packaged well. But anyway, this is sent into space, and then it is able to generate heat over time, and then that heat can be harvested as electricity. So using a thermophotovoltaic approach. And so what is different about thermophotovoltaics compared to photovoltaics? This is just a brief summary of the key differences. So, of course, as you know, the photon source in photovoltaics would be the sun, which travels over 1 astronomical unit, which is about 150 million kilometers into your PV cell. And the PV cell usually has band gap, usually a little over 1 electron volt. In thermophotovoltaics, your thermal emitter is on the Earth. It's very close to your thermophotovoltaic cell, typically separated by a millimeter or maybe a few millimeters. And then the thermophotovoltaic cell usually has a band gap below 1 electron volt in order to get the highest efficiency. So now, of course, if you just do this naively, then the efficiency is going to be very low. In the first experimental demonstration, as I understand it, in the 50s, the so-called solar battery or photovoltaic cell made out of silicon had just been demonstrated. And so then the idea was from this gentleman, Colm at Lincoln Labs, to basically put this very close to a campfire and then use the campfire to power the solar battery, now known as solar cell. And of course, it can give you some power from that approach, but the efficiency is really, really low. So we need a better method of generating thermal emission and then harvesting it as electricity. And so definitely reducing the band gap is usually very helpful for most reasonable temperatures. But then a second approach actually is to use photonic crystals or other types of selective emitter structures to actually shape the thermal emission spectrum before it reaches the photovoltaic cell in the first place. And so if you don't do that, then you can see in this picture on the left that the efficiency is going to be very low because you emit some wavelengths that are useful, but many are absorbed and then generate waste heat. Okay. And then others can be reflected off to the side, and you can have other types of losses. Now, if you have a photonic crystal, on the other hand, or another selective emitter for that matter, then what it can do is basically reduce the emissivity at wavelengths that are energies or correspond to energies below the band gap of the receiver. And you can also recycle some of the emitted light back onto the emitter itself, so then you can reuse that heat for another triad emission. And there's a paper from about 6 years ago that actually explains all the details of how this works. And in particular, there's a numerical model that we constructed to show how the system should behave over a very, very broad range of material choices. And so this model is just looking at the emission as a function of wavelength, which is based on the black body, times this emissivity function, which depends on both the emissivity at a certain angle, integrated over like the whole range of angles. And then the output of the thermophotovoltaic system depends on the emission. Okay. And so this ISC is what determines the emission property. So that's the first term of the current voltage relationship. And so this depends on the emission times this external quantum efficiency for the photovoltaic cell. So of course, any wavelength that's too long would essentially have EQE of 0. And then times both the direct absorption as well as any like multiple reflection absorption, which is shown here. And then in the IV curve, we also have non-radiative and radiative recombination terms, which are thermodynamically required for photovoltaic cells. Of course, this is not a solar cell course, but there are also lectures available from Mark Lundstrom and Ashraf Alam on YouTube, which you can look at if you want more details on how that works, and on NanoHub. And then there's another factor which I mentioned previously, which is basically photon recycling, where the long wavelength photons that aren't absorbed are actually being bounced back to the emitter. And then this is actually quantifying the impact of that reabsorption. And then to get the overall efficiency by which you're able to convert that input heat into final electric output, we have basically this set of equations where we have the power output of the photovoltaic cell, which is a product of short circuit current, open circuit voltage, and fill factor, which is well known for solar cells, divided by the emitted power, but then corrected by the reabsorption, which reduces the effective emitted power, but then adding the enthalpy of heat loss if there is any heat loss in the heat generation process, if you will. So that gives us a very comprehensive framework for future modeling efforts. And what we find is that if you have a very high performance system, so in other words, you have very high emissivity at target wavelengths and then very low elsewhere, and good photon recycling of errant photons and so on, and you have a very close proximity of the emitter and receiver, and so several other conditions, and also you have high quality gallium antimonide thermophotovoltaic cells, which may be a band gap around 0.7 EV, and your emitter is on the order of 1200 C. Then we find that the efficiency will increase as a function of TPV band gap and temperature in kind of almost a linear fashion. But there's always going to be kind of an optimal range of band gaps for any given emitter temperature. And like I said, 0.7 EV is a common choice for operating temperatures between maybe 900 to 1200 C, which is a fairly typical range of temperatures that you could achieve. And the best system that I'm aware of at the moment has a 23% efficiency at about 1050 degrees Celsius. But if you approach these limits of performance, then you could actually get more than double of that performance, or about 52%, using still a reasonable temperature. And then if you're willing to go to even higher temperatures, although of course that's very difficult, then you could even have more than 52%. In the next lecture, I mean, of course that was a lot, but we'll try to explain how do we feel that this is actually a valid model? Like, how can we confirm and check this, and then look at future applications?